Hello, it's Keith here, and this is lesson 1 of the simple series of my ARM assembly programming tutorials. What's the simple series? Well, in this series we create a single ASM file that is basically a demonstration of something on the system, and in today's example we're going to be looking at how to create a simple 8x8 sprite, that little smiley there, and we're going to be able to move it around the screen with the cursor keys. And you can see we're checking the boundaries of the screen to make sure it can't go off the screen. And the idea of this is you could use this as a building point to start making a little game like a Pong game or some kind of shoot or something. So hopefully it's a nice, easy, realistic getting started point for you to build on and make something of your own. That's the idea anyway. So we're going to go over to the source code and we're going to take a look. Okay, so here is the source code for today's example. If I just get my mouse cursor back, the emulator was just stealing it there. So this is today's example. Now you can see the source code here, and we've got a bitmap file, and the bitmap is a smiley. Now in this case, I've defined it as bytecode here. The screen mode we're using today is the 16 color mode. RiscOS does support a 256 color mode, but I tend to prefer 16 colors because I work in a lot of very old systems where 16 colors is a positive luxury. So you know, 256 is quite excessive in my mind. Now we've specified the bitmap as byte data today. You can see it just here, but you can create your own with my accurate sprite editor as a file. You can see it here. This is a free open source program that I wrote and I use in all of my tutorials. So any system that I cover in my tutorials, you can export using this editor because this is all I use. So here's today's example, and if you go to the ARM menu here and you go to RiscOS, you can export in the file formats for the 16 color screen that today's example uses, or the 256 color screen as you prefer. So that's what you can use. Now I converted it to byte data here, text byte data, but you can include a binary file instead. Now the interesting thing about the file format, if you are creating it yourself, is the nibbles are actually backwards. Now each of these nibbles represents a color, but the nibble on the left is actually the pixel on the right, so the 2 pixels are swapped around in the byte. I don't know why. Accurate Sprite Editor will do that for you, but if you're creating your own for some reason, it's the opposite to most systems like the MSX would use in that case. But anyway, we've got our sprite there, and we've got a pointer to the sprite address here so that we can load that in later on. Now the other thing, being as we're here, we'll just discuss is we've got some variables here. We need, when we're setting our screen up, to ask the screen where is the memory for the screen. Now we have to send a command, and we've got this sequence here which will request the screen base, and it returns a set of variables here. Now the only one we actually want is screen base, which is the first one, and we've got a pointer to that there label there. We'll see that later on. We've also got our palette here. We'll discuss that in just a moment though. Okay, now our program starts at memory address 8000 in RAM here, and you can see we've got a branch straight away just jumping over this area here, which is some space allocated for the stack. We're setting up our stack pointer right at the start here. We're loading this as the stack pointer, so that's got its valid stack, and then what we're doing is we're setting up our screen. Now we're using software interrupt 0 here, which is actually the print character routine, but if we send special characters to the screen, that will do other things. Now we're sending a sequence here, setting up the screen. You can see we're setting up screen mode 9 here. We do that by writing character 22, and that's the select screen mode command basically, and then we send 9, which selects screen mode 9. You can see how to select the 256 color mode if you prefer. This is a 320 by 256 screen. A little bit strange, but that's what we're using, and we're turning the cursor off because we want total control of everything ourselves. Now what we're using is SWI31, which reads the video variables here, and we need to specify the return address for those variables. It's just a bit of memory, and that now gives us the screen base, and that is just bitmap data. We can write bytes to that area and they will appear as pixels on our screen as long as we use them right. Okay, so our screen's now on and set up. What we need to do next is get our colors set up. We've got a routine for setting our palette here. We are loading the address of our palette, and we're running this set palette routine, which is processing each one of the palette entries. Now the palette entries are in this format here. Now this is the format I use for most of my systems, but I often convert them to the native format. The native format's a little bit strange on this one, so we're actually using this format as is here. Basically this is 1 nibble per channel, so we've got 4 bits for green, 4 bits for red, 4 bits for blue, and the top nibble is unused, so we're just using 12 bits of the 16 there. Now when we want to set the palette, again we're sending weird characters to the screen. So first of all, we're selecting function 19 here, which is set palette. We're then specifying the palette number, so this will be 0 to 15 on our 16 color screen. We're then turning off the flashing mode, we don't want that. And then we need to take the 3 nibbles for our green, red and blue, and we need to set them to be the top nibble of a byte and transfer those bytes to the screen there. So we're doing that for all 3 nibbles of our color definition. So what I'd suggest is, in this case, it's going to be easiest for you to just use my function here to set your palette, I think. Sometimes I break it down and use the native format. The native format is so weird in this case that we're having to send multiple commands per palette entry. I think you're going to be best just using my sample code here as is, really. Nothing really to gain there. Okay, that's our palette routine. Now, I want to discuss next the sprite routine. Now, I think I covered this before in one of my other bitmap examples. We have used a very similar sprite routine to this before, but this one has been modified slightly. Now, this is what I refer to as an XOR sprite, although on this, on ARM, the operation is actually called exclusive or EOR. So what this means is, if we write a image to the screen, the smiley, and then we write the image to the same position on the screen, it's EOR'd with the existing screen bytes, and that means that it's inverted, and the second one removes the first one. This is a convenience for a very simple program, because it means to remove a sprite and leave the background as it was before the sprite was drawn, we just draw it twice. The downside is that if there's anything underneath the sprite, it will become kind of inverted. It's just a byproduct of this kind of sprite, but it's easier than clearing away the screen or trying to remember what was underneath. So we're EORing the current sprite pixels there. That's the way we do this in this simple example. Now, what this function does is it takes an XY position in R8 and R9, it calculates the screen address of those pixels, and then it transfers our smiley sprite to those pixels on the screen. Now, the formula we're using is the screen base, which we got earlier from that function that called the OS and asked for the screen memory base. And we're then taking the Y position times 160, Y 160. Well, 320 pixel widescreen, 2 pixels per byte, so 160, so 320 divided by 2. So our Y position times 160, that's our offset for the Y line. And then the X position, now the X position is in bytes here because there's 2 pixels per byte, but we work in bytes because it's easier in this case. So we take our Y position, we're multiplying it by 160 there, that's a typo, and then we're adding the screen base. We're using this weird MLA command, and so we're adding the screen base and multiplying the Y position by 160, and then we're adding the X position. Now, R10 is now the screen memory that we want to draw our sprite to. So what we're going to do next is we're going to transfer all of the bytes of our sprite. So we've got the height of our sprite in lines here, it's 8. We've got the width of our sprite in bytes here, that's 8 pixels divided by 2 bytes per pixel, so 4 that will be. And then we've got our inner loop here, which is copying the bytes across the screen. And what we're doing here is we're reading in a byte from our source, which is the smiley. We're loading that in just there. And then we're loading the byte from the screen, and we're EORing the two together. That's our XOR that's making the inversion of what's already on the screen. And then we're storing it back to the screen. We're then just repeating until we've done all of the horizontal bytes, and then we're moving down a line, adding 160 to move down a line, and then we're repeating for the other 7 lines. So it's a little bit long, but that's basically it. So that's the end of our show sprite routine. And basically we can use this very easily. All we do is we set our X and Y position in our 8 or 9, and we run show sprite here, and that will show the sprite. Now, we're showing the sprite at the start, but we're immediately removing it again. Remember, showing in the same position twice will remove the first draw with the second draw. So we remove the old one, and that's because we're going to test our directions and move the sprite around, and so the new position will be different. Now, we could remember the old position and use the old position to redraw the sprite before drawing the new one, but I've done it this way. Now, we're actually using keyboard here. I say joystick, but that's just because I've copied this. It's based on another example, but we're using keyboard in this case. And we're using SWI6 here to read the keyboard. It's a little bit of a tricky one. I have covered it before in the platform-specific series, but at a simple level, basically, we need to set R0 to 129, R2 to 255, and then R1 needs to be 255 XOR'd with the key code of the key we want to test for. Now this will test and immediately return, so there's no delay because we wouldn't want to delay in a game. So we're just testing to see if key 57 is pressed here and immediately returning. Now the way we check is we compare to 255. 255 means that the key is pressed, and 0 means it's not pressed. So we're testing each key here. Now, if you wanted to do other keys like space and enter, you'd need to check the key codes. You'd need to check the RiscOS documentation to see what the key codes for the keys you wanted to test are. But what we're doing here is we're testing up, down, left and right, and then if the key isn't pressed, we're skipping over the next section. So this section is only happening if the, in this case, up key is pressed. What we're doing next is we're checking the coordinate, the X or the Y position, and we're checking it to the boundary and seeing if we're already at the far boundary of the screen. So in this case, the user's pressed up. Well, are we already at the very top of the screen? And if the answer is yes, then we don't want to go any further up because we'll end up rolling around, or even worse, possibly corrupting our screen, our memory of our program or something. So if we're already at the boundary, we're skipping over the movement command. But if we're not, then we're actually, in this case, moving up one line. And if you wanted to move faster, you could subtract 4 or something like that. So that's up. We're then doing the same for down, testing the down key. This time we're comparing to 256 minus 8. The screen's 256 tall, minus 8 because there are 8 lines for our sprite there. So that's the boundary there. And then we're doing the same for left and the same for right here. Now 4 because it's 4 bytes wide. So these are the checks for each of the keys in each of the directions. So when we get down to here, we've got a new position for our smiley, just depending on if any keys were pressed, and it might not have changed if the key was pressed but we're already at the edge of the screen, but we're drawing the new position. And then the last thing we've got here is a little delay. This is just to slow the game down because otherwise it'd be far too fast and you'd press right and you'd immediately end up at the far right of the screen, because these systems are very fast actually, you know, compared to the 8 bits I'm used to. A very crude delay there. And then once we've done our little delay, we just jump straight back to the start of the loop here. This is an infinite loop, and that's it really. That would be our game loop if we had a game. We've only really got a very simple example, but that's it. As I say, a nice little simple thing. It's not too long. It's, you know, there's a fair bit of code to it, but I've tried to make it as minimal as possible. And I think I think it's a good example if you're looking to do some graphics and you're looking to do some input, and you know, hopefully it'll get you started a little bit easier. Well, there we go. That's what we're covering today. Now, as I always say, if you go to my website, you can download the source code for today's example, and you can have a go with it. And not just the source code. In fact, you can download the build scripts and everything else as well. So hopefully you can get started pretty quickly. Now, as I always say, you're welcome to use them in any way you can. You know, if you manage to make something amazing out of them, you're welcome to do so. And if you manage to make loads of money out of it, you don't need to give me credit. Just have some fun with it. I'm sure you've earned it. So use my source code in any way you benefit from. Anyway, I hope you've enjoyed this. If you have, hit the like button and hit the subscribe, because there'll be more RiscOS coming, I'm sure, at some point. And if you like the videos, YouTube recommends them to other people, so that really helps me out. Anyway, I hope you've enjoyed this. Thanks for watching today. If you've enjoyed this video today, please consider supporting my content. It takes 20 to 30 hours a week to keep making these videos. It's basically all I do when I'm not doing my day job, and it's only through the support of my patrons and the other sponsors that I'm able to continue justify doing it, essentially. You can back me on Patreon. I post a weekly update with the latest work on the current projects I'm doing. You can see one here, and also the newest videos. There's a large backlog of videos that are currently only available to the patrons, although they will all be available to everyone later on. And also it's the backers who I ask when it comes to making decisions on how to change the content in the future, what new content to create and things like that. You can see there was recently a survey of the backers, so I can plan next year's content. As well as Patreon, you can now become a member of my channel on YouTube. There's a join button you should see just below this video. You can use that. YouTube backers get the same content as Patreon. I just post it through the YouTube interface instead of the Patreon one. It's the same content every week. Also, if you prefer, you can go to my Teespring store and you can get some Chibi Akuma's merchandise or some Learn ASM merchandise if you prefer, if that's how you would like to back me. Links for all three are in the description of this video below. Anyway, whatever you decide to do, I hope you've really enjoyed this video. Thanks for watching today, and goodbye.